Welcome back to Geometry, Measurement, and Probability. In this video, we're going to look at section 9.2, and we're picking up in the second half of section 9.2 with multi-stage experiments with replacement. Now, in our last video, we talked about independent events. Independent events do not influence each other. Dependent events do. For instance, let's suppose we have a box that has 2 white marbles and 1 black marble. But this time, we are drawing the marbles without replacing them. Let's look at our probability tree, and we're going to label our probabilities. On our first draw, we could draw a white ball or a black ball. And on the second draw, we could also draw a white or a black. And so our possible outcomes would be a white and a white and a black and a white, or a black and a black. Now, let's think about our probabilities. First, I need to know how many total balls there are. 2 white plus 1 black gives a total of 3 balls. So our probability of drawing a white, there are 2 whites out of 3 total balls. That would give us a probability of 2/3. There is 1 black ball out of 3 total balls, gives us a probability of 1/3. Our denominator of our fraction changes when we think about the second ball. This time we are not replacing the ball that we drew out the first time. So now we have only 2 balls left. We started with 3, we took out a ball, so we have 2 balls left. If I drew a white ball the first time, there were 2 white balls to start with. I've already taken 1 out, so that leaves me with 1 white ball out of 2 total balls. Now if I drew a white ball the first time, I still have 1 black ball left and 2 total balls. Now what if I drew a black ball on the first draw? Well, if I drew a black ball the first time, I have 2 white balls left and I still have 2 balls. If I drew a black ball the first time, there are no more black balls left in the box. And so I have 2 balls left. So the probability of drawing a black the second time, if I draw black the first, is 0 out of 2. So notice my probabilities changed with the first and second draw when I do not replace the balls. Now to find the probabilities, I follow the paths on my probability tree and we multiply just like we did before with our other multi-stage experiments. With the outcome white times white, follow your path, we have 2/3 times 1/2. Multiply and the 2's cancel out since 1's in the numerator and the other 2 is in the denominator. We have 1/3 for our probability. For a white and then a black, we have 2/3 times 1/2 when I follow the path on the probability tree. The 2's cancel out and that leaves me with 1/3. For black then white, follow the path on the probability tree and multiply the probabilities. 1/3 times 2 over 2, again the 2's cancel out since 1's in the numerator and the other 2 is in the denominator, and we have a probability of 1/3. Finally, black and black, follow your path on the probability tree, so we have 1/3 times 0 over 2. 1 times 1 is 0, and 3 times 2 in the denominator is 6. 0 over 6 gives us 0. Now, let's look at example 6. Let's look at the box that has the letters of the word probability. We have 11 letters. We're going to draw 4 letters from the box, again, without replacement. And I want to know what's the probability that I draw the word baby in that exact order from the box. So first we have 11 total letters. There are 2 B's, and so I have 2 out of 11 for the first B. Now notice we are drawing the letters and without replacing them. With a multi-stage experiment, we multiply our probabilities. Since I don't repeat the letters, I still have one A, and notice this time I have only 10 letters left. I took a letter out, and so that leaves me with 10 letters. The 2 out of 11 is the probability of the B, then 1 out of 10 is the probability of A. So let's look at that second B. We have one B left in the box out of 9 letters now. We've taken out 2 letters, so we have 9 letters left. And then last, we have Y. There's one Y in the box over 8 letters left. And so our probability would be 1 over 8. Notice again, with a multi-stage experiment, we multiply our probabilities. 2 goes into itself 1 time and into 10 5 times. Multiply your numerators gives us 1. Multiply the denominators gives us 3,960. And so our probability is 1 over 3,960. Look at example 7. We have an urn that has 4 red marbles, 3 white, and 1 blue. Again, notice that we're drawing the marbles without replacement. In part A, I want to know what is the probability that both marbles are red. We have a total of 8 marbles, 4 red plus 3 white plus 1 blue. The probability that we draw a first marble red, there are 4 out of 8. Multiply, we took out a red marble without replacing it, so that leaves us with 3 red marbles, and we have 7 marbles left because we took out a marble and didn't replace it. Multiply here, 4 goes into 8 2 times, multiply your numerators gives us 3, and multiply the denominators gives us 14. Now what if we want to know the probability that both marbles are white? There are 3 white marbles and 8 total marbles. Multiply. If we take out a white marble, we're left with 2 white marbles and a total of 7 marbles. 2 goes into 8 4 times. Multiply the numerators. 3 times 1 is 3, and 4 times 7 is 28. Now let's look at conditional probabilities. With conditional probabilities, our sample space is affected by additional information, and so this reduces the size of our sample space. So let's suppose we toss a fair coin 3 times. We have 2 events. Event A is getting a tail on the first toss, and event B is getting a tail on all 3 tosses. You'll notice our loops. Loop S is our sample space. There are 8 outcomes in the sample space. Loop A represents event A, a tail on the first toss, and then we have loop B, which is a tail on all 3 tosses. So let's suppose I want to find the probability of B, or the probability of a tail on all 3 tosses. That is 1 out of 8 total outcomes. Now look at the next one. Notice there's a line between the B and the A. That line represents given. So this tells me I am giving you some extra information that's going to reduce my sample space. There is still only 1 outcome that has a tail on all 3 tosses. But this time I have reduced my sample space to A. And so we only have 4 outcomes in A, and my conditional probability here is 1 out of 4. So here's our definition for conditional probability and some notation you need to know. The line between the B and the A represents given or given that. And then we have our intersect means A and B. So let's look at some more conditional probabilities. Let's suppose we want to find the probability of rolling a 6 on a fair die, and we know that the roll is an even number. So here's our notation. Probability of 6, the straight down line is our given, and then after that is our extra information that restricts our sample space. There's only 1 6 on the die. Now, the even is going to be our denominator. There are 3 outcomes for even, 2, 4, or 6. And so we have 1 out of 3. So notice the number of outcomes in the even was my denominator of my fraction. Let's look at another. We have a table that shows some data collected at a high school. We want to know in part A, what is the probability that a junior is selected given that the student is female? So the given that's going to tell us how many we have in our denominator. So I'll look at how many total females. We add 98 plus 101 plus 105 plus 101 gives us a total of 405 in the denominator. Again, we're considering only the females. Now we want the probability that a junior is selected out of only those females. Well, there were 105 juniors, and so that is the numerator of my fraction. Simplify your fraction. 5 goes into 105 21 times, and 5 goes into 405 81 times. This fraction will simplify further. 3 goes into 21 7 times, and 3 goes into 81 27 times. Now let's look at another one. What's the probability that the student is male given that the student is a freshman? Given that tells us how many go in our denominator. There are 103 plus 98 freshmen gives us a total of 201 in the denominator. Again, we're looking at only the freshmen. 103 of those were male. The 103 is my numerator, and this is my probability. Let's look at one more. What is the probability that a student is a senior given that the student is male? So we're going to look at just the males. There are a total of 386 males when I add that column. Again, the total number of males goes in the denominator. And we're looking at only the males. So how many males are seniors? There are 91 who were seniors. And so my probability is 91 out of 386.